Hi everyone. Today we're going to study numbers in general form. Any two-digit number, let's say the number 52, can be expressed as the 52 equals 50 plus 2. Then this 50, we can show that this is 10 times 5, grouped together, and then plus 2. Also, the number 37 can be written as 37 equals the group 10 times 3 and then plus 7. In general, any two-digit number, say AB, where A here is tens, B is for the ones, made of digits A and B, can be written as AB equals the group 10 times A, then plus B. Or simply we can write 10A plus B. On the other hand, for the number, let's say BA, in here B is for the tens and A is for the ones digit respectively. So we have 10 times B and then plus A, or simply 10B plus A. In general, a three-digit number, ABC, whereas A for the hundreds, B for the tens, and C for the ones, made up of digits A, B, and C, is written as ABC equals the group 100 times A plus the group 10 times B, and then plus C. Or simply we write 100A plus 10B plus C. For example, the 351, we can show that this is 300 plus 50 plus 1. And then we rewrite this as 100 times 3 plus the group 10 times 5 and then plus 1. Today we're going to study reversing the digits of a two-digit number. Let's proceed with the sum of a two-digit number and its reverse. When a two-digit number, say capital N, equals AB, is reversed, it becomes another number, capital Q, and this is equal to, from AB, it becomes BA. Then, the N plus Q equals another number, R, and this R is divisible by 11. And here's the proof. The capital N that is equal to AB, we can write this AB in general form, and that is 10A plus B. When we reverse this, it becomes capital Q. From AB, we write BA. Then this BA in general form is 10B plus A. Thus, when we have N plus Q, we will write the AB plus BA. Now let us show the general forms of these numbers respectively. The AB is 10A plus B plus the BA, that is 10B plus A. When we remove the grouping symbols and combine like terms, 10A plus A is 11A plus B plus 10B. That will be 11B. In here, we can see that 11 is a common to both terms. We can factor it out. So we will have 11 times the quantity A plus B. This is now the new number, and that is R. We see here that 11 is a factor of r. Thus, r is divisible by 11. Example, show that the sum of 49 and its reverse is divisible by 11. So we have this 49 plus the reverse is 94, and the sum is 143. When we divide this by 11, the quotient is 13. Notice that the quotient is 13, a whole number, with 0 remainder. And in that case, we say that the sum of 49 and its reverse is divisible by 11. What about the difference of a two-digit number and its reverse? So when a two-digit number, say capital N equals AB, is reversed, it becomes another number, capital Q, and this is represented as BA. Now suppose we have N minus Q. This is equal to capital R, and this R is divisible by 9. Here is the proof. The capital N, that is the number that is equal to AB. And we can write this as a general form, 10A plus B. When we reverse this, N becomes Q, and the AB becomes BA. In general form, this is equal to 10B plus A. Now let us show that N minus Q, and this is AB minus BA. Let us show the general forms of AB and BA respectively. So we have the group 10A plus B minus the group 10B plus A. Let us simplify this. When we remove the grouping symbols, let us combine like terms. So this 10A minus A, we will get 9A. And this plus B minus 10B, we will get negative 9B. For the two terms, the number 9 is common. We can factor it out, multiplied by the quantity A minus B. And this new number is the R. We can see that 9 is a factor of R. Therefore, R is divisible by 9. Example 1. Show that the difference of 71 and its reverse is divisible by 9. So we have this 71 minus the reverse is 17. Now the difference is 54. When we divide this by 9, the quotient is 6. Note that the quotient is 6, a whole number with 0 remainder. Thus, the difference of 71 and its reverse is divisible by 9. Example 2. Show that the difference of 29 and its reverse is divisible by 9. So we have 29 minus the reverse, it is now 92. The difference is negative 63. When we divide this by 9, the quotient is negative 7. We can see here that the quotient is a negative 7 with 0 remainder. Then we conclude the difference of 29 and its reverse is divisible by 9. Today we're going to study reversing the digits of a 3-digit number. Given a 3-digit number, let's say ABC. In general form, this ABC equals 100A plus 10b plus c. Now, let us reverse this 3-digit number. So we have now CBA. The C in the ones originally becomes in the hundreds position, while the A in the hundreds becomes the ones digit. When we write this in general form, we have now 100C plus 10B plus A. Note that the digit tens, which is B, is the same for the two numbers. Now let us subtract the numbers. So this is ABC minus CBA. When we show the corresponding general forms of the numbers, we have like this. Now let us simplify this expression. When we remove the grouping symbols, then we combine like terms. So 100A minus A, we will get 99A, and then 10B minus 10B becomes 0, and then C minus 100C. The number 99 is common. We can factor it out. So we have 99 times the quantity A minus C. Here we see that the difference is divisible by 99. Example 1. Think of a 3-digit number. Let's say 349. Make a new number by reversing the digits, so it becomes 943. Subtract the smaller number from the larger number. Divide the difference by 99 and show that the remainder is 0. So we have 943 minus 349. The difference is 594, and we divide this by 99. The quotient is a whole number 6, and note that the remainder is 0. Then we say that the difference is divisible by 99. Example 2. Show that the difference of 813 subtracted by its reverse is divisible by 99. We write the 813 minus the reverse, so that is 318. The difference is 495. When we divide this by 99, the answer is 5, with remainder 0. Now we say that since the difference 495 divided by 99 equals a whole number and remainder is 0, then 495 is divisible by 99. Example 3. Show that the difference of 518 subtracted by its reverse is divisible by 99. The number given is 518 minus the reverse, which is 815. The difference is negative 297. When we divide this by 99, the quotient is negative 3. Note that the remainder is 0. Then we conclude, since the difference negative 297 divided by 99 equals an integer and remainder is 0, then negative 297 is divisible by 99. Today we're going to study shuffling a 3-digit number, let's say ABC, into CAB, and BCA. Given a 3-digit number ABC, let's shuffle the digits into CAB and BCA. For example, the given number is 237. We shuffle this into 723 and 372. In general form, let's say the number ABC, this is equal to 100A plus 10B plus C. What about the CAB? Equals 100C plus 10A plus B. And the number BCA equals 100B plus 10C plus A. Suppose we add the three numbers ABC plus CAB plus BCA. Therefore, we're going to add the general forms of these numbers respectively, just like this. When we remove the grouping symbols and we combine like terms, we will find out the answer is 111A plus 111B plus 111C. The number 111 is common to the three terms. We can factor it out. So we have 111 times the quantity A plus B plus C. If we show the prime factors for this 111, it becomes 37 times 3 times the quantity A plus B plus C. That means the sum of these three numbers is divisible by 37. Example 1, show that the sum of 237, 723, and 372 is divisible by 37. So we are going to add the three numbers, and the sum is 1332. When we divide this by 37, we should get a whole number, and that is 36. Note that there is no remainder in the quotient. The remainder is 0. Thus, the sum of 237, 723, and 372 is divisible by 37. Example 2. Show that the sum of 632, 263, and 326 is divisible by 37. Let us add the three numbers. And the sum is 1221. When we divide the sum by 37, the answer is 33. Note that the quotient is a whole number with 0 remainder. Thus, the sum of 632, 263, and 326 is divisible by 37. Today we're going to study letters 4 digits. Here we have puzzles in which letters take the place of digits in an arithmetic sum. And the problem is to find out which letter represents which digit. It is like cracking a code. Problems given are that of addition and multiplication. There are two rules of the puzzle. Number 1, each letter in the puzzle must stand for just one digit. Each digit must be represented by just one letter. The first digit of a number cannot be 0. This is the second rule. That means we write the number 63 as 63 and not as 063 nor 0063. Finally, the general rule, the puzzle must have just one answer. Example 1. Find Q in the addition. We have here 3-digit number plus another 3-digit number, and the sum is 501. So we have 31Q plus 1Q3. There is only one letter Q whose value is required. So let's begin with this column. In the column for ones, this is the Q plus 3 equals 1. For this to happen, the digit Q must be 8. And the puzzle is solved. When we substitute the value Q as 8, it becomes 318 plus 183 equals 501. And this is correct. Therefore, Q equals 8. Example 2. Find A and B in the addition. A plus A plus A all over BA. There are two letters whose values are required. We can see the A and B. In the ones column, the sum of 3 A's is a number whose ones digit is A. This happens only for A equals 0 and A equals 5. For the two cases, let's see case 1, when A equals 0. When we try to substitute this value 0 to the A, then B equals 0 also, which is not acceptable as per the rule. That means we go to case 2, when A equals 5. When we substitute 5 here, we will get the value of B equals 1. Now it is acceptable. That means 5 plus 5 plus 5 all over 15. So we have A equals 5 and B equals 1. Example 3. Find the digits A and B. We have BA times B3 all over 5, 7A. We can see here that there are two letters whose values are required, the A and B. Note that the B here are on the tens digit for the two factors, and there is an A as ones digit for the first factor and another A in the ones digit of the final product. Now let's start in here. Since the ones digit of 3 times A is A, it must be that A equals 0 or A equals 5. In these two possibilities, the product must be 570 or 575. Now let us find B. Let us do trial and error. Suppose we assume that B equals 1. Two products are coming for 10 times 13 and 15 times 13. And both products are less than 500. That is not equal to our product here. Now suppose we assume that B equals 3. Two products will be 30 times 33 and 35 times 33. And both products are more than 900. So again, this is not equal to our assumed product 570A. That means we can assume that B equals 2. If that is the case, there will be two products, 20 times 23, and 25 times 23. The first product is 460, while the second is 575. And this is what is acceptable in our case. That means A equals 5 and B equals 2. This is the answer. Today we're going to study divisibility by 10, 5, and 2. Let's define divisibility. A given number, capital N, is divisible by another number, small n, if the quotient has 0 remainder. Let's see now divisibility by 10. A number is divisible by 10 if it ends with 0. Here is the proof. Let capital N equals ... CBA. We have here 3-digit number, but the 3 dots in the front of CBA represent some arbitrary digits. If we write this in general form, we will have like this: ... plus 100C plus 10B plus A. Since 10 and 100 and so on are divisible by 10, so are 10B, 100C, and so on. And as for the number A is concerned, it must be divisible by 10 if capital N is divisible by 10. This is possible only when A equals 0. Again, we say that a number is divisible by 10 if it ends with 0. Examples: the numbers 10, 200, 5,000, 25,900 are divisible by 10 because they end in 0. Example 2, the numbers 17, 228, 7,403, 12,645 are not divisible by 10 because they do not end in 0. Divisibility by 5. A number is divisible by 5 if it ends with 0 or 5. Here's the proof. Let capital N equals ... CBA, a 3-digit number. But we know that these 3 dots represents some numbers in front of the CBA. We can write this in general form. So we have ... plus 100C plus 10B plus A. Since 10 and 100 and some numbers are divisible by 5, so are 10B, 100C, and so on. And as for the number A is concerned, it must be divisible by 5 if capital N is divisible by 5. This is possible only when A equals 0 or 5. So we say it again. A number is divisible by 5 if it ends with 0 or 5. Examples: the numbers 10, 25, 705, 2,595 are divisible by 5 because they end in 0 or 5. Another example: the numbers 17, 22, 7,403, 1,264 are not divisible by 5 because they do not end in 0 nor 5. Divisibility by 2. A number is divisible by 2 if it ends with 0, 2, 4, 6, and 8. Or we can say that an even number is divisible by 2. Here's the proof. Let capital N equals ... CBA. In general form, we write this as ... plus 100C plus 10B plus A. Since 10, 100, and so on are divisible by 2, so are 10B, 100C, and so on. And as for the number A is concerned, it must be divisible by 2 if capital N is divisible by 2. This is possible only when A equals 0, 2, 4, 6, or 8. Or we say that capital N must be an even number. So we say it again. A number is divisible by 2 if it ends with 0, 2, 4, 6, and 8. Examples. The numbers 30, 52, 64, 156, and 448 are divisible by 2 because they end with 0, 2, 4, 6, or 8. Or we say that these examples are even numbers. Second example, the numbers 23, 45, 77, and 861 are not divisible by 2 because they do not end with 0, 2, 4, 6, nor 8. Or we say that these examples are odd numbers. Today we're going to study divisibility by 9 and 3. A number is divisible by 9 and 3 if the sum of its digits is divisible by 9 and 3. Let's say we have a 3-digit number, say CBA. We can show the general form of this number as 100C plus 10B plus A. Now we can rewrite this expression into like this. We split the 100C into 99C plus C, while the 10B we split as 9B plus B. Then we group C plus B plus A. For the other two terms, we can group this and we factor out a common number, which is 9. So we have 9 times the group 11C plus B, plus this group C plus B plus A. We can see here now that we have two groups. The first group has a factor of 9. That means this first group is divisible by 9. And for this second group, the C plus B plus A, the sum must be a multiple of 9. Or we say that the sum of digits must be divisible by 9. Now, if a number is divisible by 9, it is also divisible by 3. Let's see example 1. Check the divisibility of 21,436,587 by 9. To check this, we're going to add the digits So we have 2 plus 1 plus 4 plus 3 plus 6 plus 5 plus 8 plus 7. And the sum is 36. We know that 36 is divisible by 9. So, since 36 is divisible by 9, then the number 21,436,587 is divisible by 9. Example 2. Check the divisibility of 152,875 by 9. We add the digits, so we have 1 plus 5 plus 2 plus 8 plus 7 plus 5. And the sum is 28. And we know that this 28 is not divisible by 9. Then we conclude, since 28 is not divisible by 9, then 152,875 is not divisible by 9. Example 3. If the 3-digit number 24x is divisible by 9, what is the value of x? Note that the x is in the ones digits of this 3-digit number. Since 24x is divisible by 9, the sum of its digits should be divisible by 9. So we can show that 2 plus 4 plus x must be divisible by 9. We can simplify or add the 2 plus 4, so we have 6 plus x. The sum must be 9 or a multiple of 9, let's say 18 or 27 or and so on. But x here is a digit in the ones, so that means there's no other way but x should be equal to 3. So when we write this x as 3 in the number, the 3-digit number is 243. So the value of x is 3. Example 4. Check the divisibility of 2,146,587 by 3. Let us add the digits 2 plus 1 plus 4 plus 6 plus 5 plus 8 plus 7. And the sum is 33. We know that 33 is divisible by 3. Then we conclude that 2,146,587 is divisible by 3. Example 5. Check the divisibility of 15,287 by 3. Let us add the digits 1 plus 5 plus 2 plus 8 plus 7. And the sum is 23. But this 23 is not divisible by 3. Then we conclude 15,287 is not divisible by 3.